Right, so this is the second and final part of the talk. So here we'll be talking about the Pan-Levy-6 differential equation and how some solutions of it are related to these equivariant instantons. All right, so first of all, let's talk about what the Pan-Levy-6 equation is. It's a famous nonlinear second-order differential equation for a complex valued function of a complex variable. And the equation looks like this. It's second order, involves a second derivative, first derivative squared, so it's clearly nonlinear first derivative. And then it involves, and of course you can see it's highly nonlinear by the way the argument appears in here. And it involves four complex parameters or four complex constants. So we'll call this PVI. VI stands for letters for Roman 6. Depending on theta, where theta is a vector of four complex numbers, or vector in C4. And here's how these four numbers appear as parameters in the differential equation. So when you talk about a solution of Pan-Levy-6, you talk about a solution of Pan-Levy-6 for some choice of four constants here, or choice of a vector in C4. So we'll use this notation. Capital lambda consists of a pair, a solution of a complex function of a complex variable. That is a solution of the differential equation, and the theta, which is a set of parameters for which it's a solution. So we'll use this notation to include both those things. And an interesting thing, which is very important for us for Pan-Levy solutions, is there's these Schlesinger-Okamoto transformations, which are an infinite family, a discrete infinite family of transformations, which take one solution of an equation with one parameter to another solution where it's a different equation, where it's a different function, and it solves a Pan-Levy for a different value of parameters. So we'll talk more about those. And these Schlesinger-Okamoto transformations act on this. First of all, they change the function here to a different function, and they change the parameter to a different parameter, C4, and described this way, they actually act by an affine Weil group, D4, on the C4 where these parameters live. Okay, and there's the action on these things is an explicit nonlinear action. We'll give some examples of this later on. Right. So we need to remark to connect with the literature about what I'll call classic Pan-Levy-6. So sort of the older and still widely used notation, the original notation was instead of using these four values, theta 1 through theta 4, this particular combination is used. And when you do that, it has the advantages of appearing more simply in here rather than substituting each of these nonlinear looking terms, but it has a disadvantage, or another way of saying it, the previous version has an advantage, that the Schlesinger-Okamoto transformations actually act affinely by this affine Weil group on the thetas, but they don't act very nicely on these. So a nice reason if you're studying Schlesinger-Okamoto is to replace these with these combinations, and then on that set of thetas, they act better. And so sort of a necessary but painful part of working with Pan-Levy equations, you always have to figure out what notation someone is using, figure out how your constants are related to their constants, and so forth. All right, so the algebraic solutions of Pan-Levy-6, as I mentioned in the introduction, are very unusual. They're atypical. They certainly exist, but a typical solution, generic solution, is a highly transcendental function living on a universal cover of CP1 minus a singular 0.01 infinity. So that's basically a infinitely branched Riemann surface over this non-compact. And if a solution is algebraic, if it passes to a finite branch cover, if you can drop it, you can factor it through a finite branch cover, and a finite branch cover branch over these points is a compact Riemann surface. In fact, it's a special form of compact Riemann, so sort of belly curve. And so the algebraic solutions, they do exist, but they're very rare. There was a flurry of activity on this in the 90s. Dubrov and Mazzucca found a very interesting collection of algebraic solutions, and Hitchin then did some very interesting work, part of which I'll be building on here, and Bolch actually did a lot of work following that, also found a lot of solutions. And sort of eventually, some years later, Lifsovy and Tiki did a classification by classifying certain orbits of an infinite group. They found what all the possible algebraic solutions are of Pan-Levy-6, and there's a fair number of them. There's several infinite families. discrete infinite families, and there's a couple dozen sort of single solutions. But the interesting thing is by the time S01T05 did this, all of these solutions have been found by various other methods. So in fact, the expectation might have been when you do a classification, you would find something that wasn't known before by the scattershot methods that people had employed. But in fact, by the time they did the classification, they found everything was already known and nothing else is going to be found from then on. Okay. So for us in this work, the starting point in the connection of Panelovay 6 is one of Hitchin's geometric constructions, which dates back to paper in 95, which starts exactly in the situation we're interested in. You look at SL2 acting on P3 with open dense orbit, as we discussed previously. Then what Hitchin considered is lifting this action to the trivial bundle of rank 2. What does that mean? That means you take a P3 product with the two-dimensional irreducible representation. That's a rank 2 bundle, trivial rank 2 bundle. And then you just act trivially, do the product action on the product P3 across this representation. So it's a lift to a trivial vector bundle, but it still acts non-trivial on the vector bundle, but acts in a fairly simple way. So it acts the same way on each fiber. Okay. Then what Hitchin did from that is by essentially inverting the Lie algebra that acts on both those things, he produced a flat connection that's log singular. There are some places where the orbit isn't three-dimensional, singular there on this trivial rank 2 bundle. And so basically the singularities of this are at the places where the two-dimensional and one-dimensional orbits are. On the three-dimensional orbits, it's a flat connection, but it doesn't extend to the whole thing because of the orbit isn't always three-dimensional. And the flatness comes basically from the Lie algebra. The integrability of the connection comes basically from the fact that you're looking at the Lie algebra. Then what do you do? Then you say, okay, well, P3, that has lines, that has projective lines in it. So if I restrict this flat meromorphic connection to a projective line, I get a connection on a CP1, which has generically, it has 4 singular points, and each of those is a simple singularity. And so it's a log singular connection on a P1. And I say, okay, that's great, but I have lots of P1s and P3. What if I deform my P1? Then I will typically get, something where the 4 singular points are not in the same place, but the monodromy is the same because it comes from a singular connection, a flat singular connection on the bigger space. And so you produce what's called an isomonodromic deformation. An isomonodromic deformation is a family of bundles on P1 with flat meromorphic connection. And when you go through the family, you deform one of the P1s. Typically, you deform the positions of the poles, but the monodromy stays the same even though you're deforming the poles. And from explicit constructions of isomonodromic deformations, Jimbo and Miwa had worked out a way that you can construct solutions of Panelovay 6 if you have this. So basically what Hitchin did on this bundle, this trivial rank 2 bundle, worked out what this meromorphic connection is, then worked out what the restriction to a line looks like, took a one-dimensional family of lines, and worked out the isomonodromic deformation, and from that, using Jimbo Miwa, found explicit solutions of Panelovay 6. So really, I think he only did one, but there's 2 that you can do by changing one of the parameters. So I'll say he did 2. And what I've done is generalize this to the case where you have the non-trivial SL2 equivariant instanton bundles on P3 that we had talked about in the last talk. So remember, there's one of these for every M0. So the 0 is the Hitchin product case. The 1, 2, 3, so forth are the non-trivial equivariant instanton bundles, which are not untrivial bundles. And you can repeat the construction of Hitchin's sort of conceptually, it's fairly simple, but practically it's actually a lot of work to do it. So for each M, the SL2 acts on one of these P3s. That was the, for each M, the SL2 acts the same way on P3 with open dense orbit, but for each M, you can lift it here, rank 2 bundle EM, which is non-trivial except for the M equals 0 case, which Hitchin did. And for each M, you can follow Hitchin's construction and still produce a flat log singular connection on this bundle. And basically you do that by looking at the monad, seeing how the Lie algebra acts on the monad, inverting that. It's technically kind of a pain, but conceptually not that difficult. And then you play the same game. You say, okay, once I have this flat log singular connection now in a non-trivial bundle described in terms of the monad, I can look at a restriction to a projective line, and then that'll give me a flat log singular connection on the projective line. I can deform that line. That'll deform the positions of the poles typically, produce an isomonotropic deformation, and then use a Jimbo-Miwa construction to again find solutions of Pain-Levé 6. And they'll be different because these bundles are different for each M. Okay, so for each M, you can construct a pair of explicit solutions, which we'll call lambda M plus and lambda M minus. The M equals 0 case is what Hitchin did. And so what I did, I actually did this a number of years ago, and then I kind of came back to it recently. So for M equals 0, Hitchin constructed this. So I explicitly constructed these up to M equals 4, that I constructed the solutions, two pairs of solutions for M equals 1, 2, 3, and 4, and kind of stopped there because the even on a computer, the calculations got a little bit hairy, and at some point, you have to stop somewhere. So for M equals 0, this is of course Hitchin's solution, except I sort of parametrized a little bit differently, but it's the same thing. And for M is greater than or 5, you can compute in principle, but again, sort of when I first computed these things, it was in the 90s on my personal computer, and it used to run overnight for some like 10 hours to compute the M equals 4 case. So I figured it was time to stop there. And I haven't gotten back to it with more powerful computers. So let's talk about the results of what those things look like. Okay, so use that Jimbo-Miwa solution on these equivariant instanton bundles that we constructed with the equivariant monads. And so you remember there's 4-parameter vector in C4 that they depend on theta 1, theta 2, theta 3, theta 4. So if we define mu to be this combination where theta 1 is 1/2, theta 2 is 1/2, they're all 1/2, then basically all of our solutions will be some scalar multiple of this parameter vector. And again, this is because we're using a theta notation. If we use the alpha, beta, so forth notation, it'd be a terrible nonlinear mess. And here's the theorem. So for each non-negative integer m corresponding to each of the instanton bundles, the equivariant instanton bundle yields a pair of explicitly computable algebraic Pain-Levé solutions, which we'll call plus and minus with an m there. And of course, each solution consists of a function and a parameter, a set of 4 complex parameters. And these complex parameters are scalar multiples of 2m plus 1 times this vector, 1/2, 1/2, 1/2. So that all the 4 parameters are the same, but they're, depending on m, they're different. So notice this one's plus 2m, this one's minus 2m. And these do depend on m. So all of these solutions for each m, you get 2 solutions, and all of these solutions have different, satisfy different Pain-Levé equation with different choice of constants. Now, each of these solutions for every m, and this is for every m, I'm not limited it to a finite case now. For every m, there's a computable solution which looks like this. The t variable in the Pain-Levé solution is expressed parametrically in terms of w this way, and the lambda is expressed in terms of w this way. So basically, then you implicitly have defined lambda as a function of t, and that solves the Pain-Levé equation. Okay, and so it looks like this for all of them. T is defined this way, and the lambda looks like this, common factor to all of them. Then for each m and plus, for each m and each choice of plus and w, there's a pair of even polynomials in W, which have degree at most 2m plus 1. And these are the things that are implicitly computable from the ADHM monad. So basically for each choice of m and plus or minus, you can compute the f plus and f m and gm, either with a plus or minus, plug them into this formula, and you've got your solution for Pain-Levé. So it's a theorem that this is true for all m, and that they have this property, but I've only computed these for a finite set of m. So the ones that I've computed, let me do it for a couple. So the original one, Hitchin's, in my framework looks like this. It's equivalent to Hitchin solutions. And basically the polynomials are really simple. One of them is 0, one of them is 1, one of them is 0. If you plug them into that formula, here's the solution that you get for Pan-Lavie. Here, of course, it's in W, then T is a function of W, so we implicitly define it as a function of T, and that solves the Pan-Lavie equation. So of course, all this implicit definition means it lives not quite on your original CP1, but you have to figure out what cover it lives on. Okay. So it's still a compact Riemann surface. Turns out to be a P1, still a rational curve, but not the original one. And here's the minus version of Hitchin's thing, the other pair. Similar thing again, these are about as simple as can be. These two swap places. When you plug it into the formula from the theorem, it looks like this. Now the first non-trivial one, this corresponds to the sort of the classic instanton of Chern number 1, also called the null correlation bundle in mathematics terms. So the first one looks like this. Again, these are very simple. And in fact, you'll notice this one actually looks like one of the previous ones, which is kind of coincidence. I'm not sure why that happens. And this one is, sorry, I did this twice here. Here's the polynomials for the 1 minus, and here is the solution that you get. So as you go up, remember from the theorem, the degrees of these things get higher and higher and higher. And so I've computed them up to m equals 4. So I'll do one of these I'll leave off the ones for 2 and 3 and do one of them, the plus 1 for m equals 4. I've computed both these. I'll only display this one. So the plus 1 here looks like this. Here's the parameters in the Pan-Lavie equation, and the polynomial is a polynomial. I'm sorry, you can cut it off here. Goes roughly up to here. I think it goes up a couple more terms. I'm not sure if it cuts off here. But anyway, here's an explicitly computed polynomial, which of course you need to compute on the computer. It's got huge coefficients. Here's the other one. Plug those into that formula in the theorem. You get an explicit solution of Pan-Lavie. You can check satisfies Pan-Lavie. I won't write it out because it's even worse rational function than its polynomials. So from these, you can easily construct a solution, check that it's a solution. And I'm omitting the similar expression for the minus m equals 4 solution, but I've computed all those. Okay, so here's sort of the thing that I'm interested in. So fine, you can compute all these Pan-Lavie solutions. And then you also remember that there's Schlesinger-Archimedes transformations between solutions of Pan-Lavie. And so the claim is, and this is done by explicit computation, that these solutions that I've computed, and I've literally computed 10 of them up to m equals 4. So 5 here, 0, 1, 2, 3, 4, 5 here with a minus sign. And this table, you might think it goes on, but I don't know that it goes on. I've computed it up to here, and you shouldn't imply a ... conjecture. I think there's a ... but I haven't proved it. And so I've identified specific Schlesinger-Archimedes transformations, B and R5, which act this way. So each of these is a involutive transformation, which means that if you square it, it goes, it's the identity. So if you go here, hit it with a B, you go this way. If you hit this with a B, you go back to here. You start here, hit it with an R5, you go this way. If you hit this with an R5, you go back to here. They're involutive. So their square is equal to 1. And so here, if you go to here, B squared here is equal to 1 identity on here. Okay. If you take, so we'll talk about these specific, we'll talk a little bit about what these are, what these look like and how they act. But if you, from these, looking at this diagram summarizes the main computational part of the paper, that we've identified specific Schlesinger-Archimedes transformations which map the specific solutions this way. They relate the solutions this way. Right? And so if you define Q to be this composition, then its inverse is this. Why is that? Because both these are involutions. Okay. And then the theorem is that you get something, these look like creation and annihilation operators. So if you do this, you look at Hitchin's solution plus, and if you look at what Q does to that, you first go with R5, then with B. If you start here, hit it with Q, you end up doing this. You go to this one. So if you hit Hitchin's 0 plus with this Q, you get this one. If you hit that with a Q, you go here, get this one. If you hit that with a Q, you get this one. So this looks an awful lot like creation and annihilation operators for the quantum harmonic oscillator. But the nth solution with a plus, you get by hitting the 0th solution m times with a particular operator. Okay? And on the bottom row, you can actually do the same thing, that this one, if you hit it with B and then R5, you go from here to here. So if you do that multiple times, you can get to any one of these from this one. And so Q minus M means Q inverse to the power M, of course, that you get another basically creation operator on here. And also the Q inverse acts as an annihilation operator in the top row, and the Q acts as an annihilation operator on the bottom. So you get two series of things which look an awful lot like the harmonic oscillator creation and annihilation operator. Okay. And so let's see the, all right. So basically when you put that together, the Qs, as we talked about from the last diagram, look like this, right? If you ignore the other Schlesinger transformations, they look like this. And you remember that each of these instanton bundles corresponds to, from each of these, you construct one of these pairs. So I drew that this way as the columns here. This reminds you these two solutions come from E0, these come from E1, and this map means, okay, you can start with a bundle, get a Panelet solution. I don't know how to go back from here to here. And so here's what this looks like. So these columns, say from each of these equivariant instanton bundles, you get a pair of Panelet solutions, and you have these specific Schlesinger-Okamoto transformations, which I checked, map these particular Panelet solutions between each other. So what this sort of suggests, and the reason I'm interested in this is, well, okay, so what you'd really like to do is say, okay, is there some operator that takes a trivial equivariant bundle to the first one, that takes this one to this one, takes this one to this one? The dotted line means I don't know if such a thing exists. Is there a creation operator which you could take and hit the trivial equivariant instanton bundle, get the next one, hit it again, get the next one? And if there is, that would of course explain what these Qs are. These Qs are then shadows of those things through the Hitchin construction of constructing Panelet solutions. I don't know if there is such a thing. I've been looking for these both on P3 and on some of the other manifolds, but this is the main interest, right? This sort of suggests maybe there is such a thing. And if there is, it'd be interesting if you construct these highly non-trivial and equivariant bundles just by hitting something with a simple operator. Okay. So let's go back to the Panelet and talk about these things a little bit more detail. These are kind of obscure topics. So we'll highlight one of these transformations. We have two that we talked about, the B and the R5. Let's just talk about R5. We picked one for reasons of space. Okay, so this R5 acts on one of these solutions. So that consists of a function and a set of 4 parameters, takes the function to itself plus this horrible expression, which is, so notice here, this is the first derivative of the function with respect to t. That's actually in the denominator and divided by the function itself with some other stuff. So this is a fairly horrible expression. And what I did is I've computed all these guys up through m is equal to 4, both the plus and minuses, and I just computationally checked that this particular transformation, which does this to the function, takes those horrible rational functions, transforms among each other this way. So this is a computational proof up to m equals 4. Okay, so non-obviously, this thing is an involution on solutions. If you take one of these things, if I put one of my solutions in here, do this horrible transformation to it, then what I get, I do this transformation again, I get back the same one. So that's by no means obvious. And that depends on the fact that these are solutions of Panelet with that set of parameters. So certainly you wouldn't expect that to be an involution, but it is because it's a solution of Panelet with those set of parameters. And it turns out, again, miraculously kind of, that's an involution. So Okamoto was, I think, a person who really clarified that these things are there. And I know it's still a bit of a mystery as far as I'm concerned, maybe not as far as some other people are concerned. So here's basically what you get. So by explicit computation, I explicitly computed these, explicitly hit it with this transformation, saw this, and I'll omit the similar description of the involutive transformation B, which relates the other part of the diagram. So there's basically two sets of things like this, two explicit sets of transformations, which let you go between the solutions. Okay, so again, I've computed them up to m equals 4, but the conjecture is, of course, that everything works for all the integers m, not just m up to 4. And the reason I've only computed up to m equals 4 because I only computed the Pain-Levé solutions up to m equals 4. In principle, I can compute a couple more, but you have to stop somewhere. But I can't compute all of them, and so I need some other method to see that this is actually true for all of them. You can't do it all by enumeration. So a couple comments on this. So from the Schlesinger-Okamoto transformations, so I checked for up to 4 that these transformations relate between them. If you go past 4, the Schlesinger-Okamoto transformations still create new additional solutions of Pain-Levé, but what I don't know if these correspond to m greater than 5, since I haven't computed the instanton solutions, I don't know if these new solutions are the same as the instanton solutions. I expect they are. They were up to m equals 4. And let's give an example. So this one I compute explicitly, also can be gotten by creation operators from the 0, 1 by hitting with 4 times. And if you hit it once more with Q, you get a new PVI solution, which is described by the polynomials. I had to truncate them because they're very high degree just to show that they're computable. Plug those into the formula for the main theorem, and you get a solution of Pain-Levé 6, which you can check as a solution, which has all the properties that a solution from the instanton E5 should give, but I don't know if it's the same as a solution for instanton E5 because I didn't compute the instanton E5, so I didn't compute the solutions directly. I compare, but I suspect that it is. Okay. So let's talk about some conclusions about where you can go with this. So really sort of the thing that struck me way back in 97 when Gil and I worked this out, is that there's only a countable set of SL2 equivariant instanton bundles on P3, and for each Chern number, there's at most 1. Sometimes there's 0, sometimes there's 1. Okay, so that's kind of an interesting structure, which again suggests some kind of combinatorial relation between things. So again, the trivial case that Hitchin worked out gives rise to the Pain-Levé solutions. And what I worked out is that the appropriate Schlesinger-Okamoto transformation, remember there's a lot of these, there's a affine D4 worth of them. So I really looked at a one generator subgroup, a Z subgroup of those, a particular one. So appropriate Schlesinger transformations should correspond to other SL2 equivariant bundles. So basically, why is that? Because when you do this, the appropriate type of Schlesinger-Okamoto transformations, and you look at the restriction to the P1s, the meromorphic connections, and the P1s with log singularities, use the appropriate Schlesinger-Okamoto transformations should give you something with the same monodromy, even though the residues of the poles are different. And so they should, hopefully they'll compactify to instanton bundle, or to a bundle, equivariant bundle over SL2. Why instanton bundles? There's no reason why they should be instanton bundles. Why should they be constructed from monads, or why should they be characterized by the vanishing of a certain sheaf cohomology? There's no particular reasons. And so I think of this as kind of like if you lose your keys on the street at night, you should look near the street light. Why is that? Because you've probably lost them near the street light? No, because if they're somewhere else, you're never going to find them. So you might as well look at the place where you're going to find them. So why instanton bundles? Because we have the tools to work with them. I can work out what the equivariant instanton bundles are. If there are other lifts to equivariant bundles, I don't know how to study them. And it turns out that there probably aren't any more. And why is that? So this is what I'll call a Goldilocks principle, that if there were other SL2 equivariant bundles, they would correspond to other solutions of Pain-Levé 6, which should be related to ours by the Okamoto transformations, and that'd just be too many solutions of Pain-Levé 6. So you expect to have some of them, again, corresponding to the appropriate Schlesinger-Okamoto transformations. But you don't expect to have too many, because then there'd be there'd be too many solutions of Pain-Levé 6, and you don't expect to have too few, because then you couldn't account for the Schlesinger-Okamoto transformations that you have. So this kind of makes you comfortable with the fact that there's just this countable set. It's just right. The number is just right. So now if you look at the other three-dimensional manifolds that we mentioned, which have SL2 action with dense open orbit, and you can study instanton bundles. So again, if you couldn't study instanton bundles, you probably couldn't say much about equivariant bundles anyway, because you get much more of a handle on instanton bundles than you can get on bundles in general. So let's look at the V5. That's one of the Mukai-Mamura. We'll leave off the V22 for now. So here's the interesting thing about that. So fine, you can construct instanton bundles on there. That's work of Kuznetsov, Firenze, Sana combination. They showed how to do these on various manifolds. And so I've been looking at the equivariant ones. I mentioned this briefly in the other set of slides. So why would you expect a similar phenomenon to happen? So I would expect the phenomenon you get a countable set of SL2 equivariant instanton bundles over V5, and basically for the same reasons that Hitchin, again, not later in 03, produced different solutions of Painlevé 6 by studying deformations of conics, not lines in V5. And again, same idea, but you have to look at conics instead of lines to get the appropriate number of poles. And so if you look at this, you say, okay, so Hitchin found these solutions Painlevé. Now, just like in the P3 case, you're going to have Schlesinger-Okamoto transformations of these. And the appropriate ones, the ones that correspond to same monodromy, should correspond to new kinds of bundles. And so from the same argument, which actually seems to work in P3, you would expect a countable set of bundles that are equivariant here. Again, at most one for any Chern number for basically the same structure as you have. So it's a little bit more complicated to work with these, but you have some technology here, and I've been working on some of the representation theory and sort of on my way. And so far, everything for the preliminary results is consistent with this, that some of the lower dimensional cases, you have exactly one where you should have exactly one, you have none where you shouldn't have any, but I haven't yet proved it for all of the different values of Chern number, but I expect that should work. And so the question that keeps me working on this is both in the P3 and the V5 case, and I expect the V22 Mukai-Mamura will work the same way. That's even more complicated, is these Schlesinger-Okamoto transformations of the Painlevé solutions. Are they just a platonic shadow of something more fundamental about the structure of these equivariant bundles? If you didn't know about this connection with Painlevé and Schlesinger-Okamoto, how could you go about explaining that there's this countable set of SL2 equivariant instanton bundles? And again, to me, this suggests that there might be something like a creation operator where you create them step by step from the trivial one, and the Schlesinger-Okamoto transformation for the Painlevé solutions corresponding. These are, I kind of use a platonic shadow. I don't really see the creation operator in the bundles. Hopefully there is one there, but I see this reflection here. So I think it's an interesting question. How do you explain this simple structure of equivariant bundles on P3 and apparently on V5 too? And I'm pretty confident it's going to happen on V22, but I haven't gotten any preliminary results on that yet. How do you explain that without knowing about Hitchin's work relating these to Painlevé equations and Schlesinger-Okamoto? There should be some better explanation than this. This is just kind of a shadow of what I believe is going to be a better explanation. All right, well, thank you very much for your attention. That ends this series of talks.